The screencast will start our unit on waves. We'll talk a little bit about the types of waves and wave properties and work an example problem at the end. A wave is simply a disturbance that carries energy through matter or space. It carries the energy by causing the particles of the medium to vibrate. The particles themselves do not move with the wave, but only vibrate, in this case, the wave we have below, up and down. So this point that I'm highlighting will be going up and down as the wave was traveling through the medium. And medium is just the matter through which waves travel. So again, there's no net displacement of particles when a wave travels through the medium, and particles eventually go back to their equilibrium positions. There's two types of waves we'll discuss. The first is a mechanical wave, and that's a wave that requires matter to travel through or to propagate. Examples would be ocean waves, waves on a string, sound waves, or our gummy wave that you guys will get to see tomorrow. The second type of wave are electromagnetic waves, and that's radiant energy or radiation. That does not require a medium. We call this type of wave light. This is just a schematic of the electromagnetic spectrum. We'll be concentrating only on mechanical waves for this unit, but talking about the electromagnetic waves in a future unit. The first type of mechanical wave we'll talk about is a pulse wave. So you can see our little stick figure here is causing this pulse wave, and that's really a wave caused by a single disturbance. So he's going to move the rope down, and that's going to cause that pulse to go through the medium, the rope in this case. The diagram below shows a periodic wave at 3 points in time. So a periodic wave is a wave whose source is continuous periodic or harmonic motion. So the particles in the medium are also in harmonic motion. The source of the periodic wave depicted in the diagrams is just the movement of the hand here, causing the wave to travel through the spring, which will be the medium. And again, the particles in the medium are staying in the same place, but the wave is traveling through the medium. A transverse wave is a wave in which the particles of the medium vibrate perpendicular to the direction of the wave's motion, sometimes called an S wave. So just like the way we saw on the previous slide, the particles are traveling up and down as the wave is traveling left or right. So for transverse waves, we have an amplitude, which is simply the maximum displacement from the equilibrium position, and the crest, which is the highest point of the wave. And then there's also a trough, that would be the low point of the wave, and the wavelength. So on a transverse wave, that's the distance between equal parts of adjacent waves. So here the wavelength is measured from crest to crest. Another type of wave is a longitudinal wave. In a longitudinal wave, the particles of the medium vibrate parallel to the wave's motion. Examples of this are sound waves and earthquake waves. These waves are also called pressure waves or P waves. So for this longitudinal wave, the wave is moving in this direction to the right. The wavelength would be from compression to compression. And again, the amplitude is the maximum displacement of a wave from its undisturbed position. So for a longitudinal wave, this is related to the rise and fall of pressure within the wave. So that difference in spacing and density and the compression from the medium and equilibrium. Another type of wave is a surface wave. So this is a wave that travels along the boundary between two surfaces. So like our example here, an ocean wave. The two surfaces being the water and the air. So particles of the medium vibrate in a circular path in a surface wave. So it acts a little bit like a longitudinal and a transverse wave. Some more wave properties is the frequency of the wave. That's the number of waves that pass a given spot in 1 second. Frequency, as you may know, is measured in hertz, and so a hertz is a 1/2 second. So again, the number of waves per second would equal that number of hertz. Second time property is period, and that is the time it takes one wave to pass a given point. And these two are inversely related. So the period equals 1 over f, or the frequency would obviously be equal to 1 over the period. So what determines the speed of a wave? Really, that's the medium that it travels through. And the speed is related by our wave speed equation, which is that the velocity of the wave equals lambda, which again is the wavelength, times the frequency. So again, the speed of the wave is the lambda times the frequency. The wavelength is going to be in meters. And then of course the frequency is in hertz. But that's also 1 over second, leading to that familiar unit, meters per second, for velocity. So if we're going to do an example problem here, we're trying to find the wavelength in air at 20 degrees Celsius of an 18 hertz sound wave. 18 hertz is one of the lowest frequencies that is detectable by the human ear, unless you've been wearing your earbuds too much, in which case you may not be able to hear 18 hertz. So the velocity of a sound wave in air at 20 degrees Celsius is 343 meters per second. So we'll use our wave speed equation, and we're trying to find the wavelength. So we'll rearrange it for wavelength equal to the velocity over the frequency. So we know that, again, the velocity was 343 meters per second. The frequency is 18 hertz. And then remember that 1 hertz is a 1 over second. 1 over second, we'll take the seconds up top. That's going to cancel out with our seconds in the velocity. Just divide 343 by 18, and you're going to come up with 19 meters for the wavelength of an 18 hertz sound wave in air at 20 degrees Celsius. All right, that concludes our screencast for the introduction to waves. There are a few questions that you need to answer on the Google form as well. And I look forward to seeing you guys tomorrow. And we'll be working on waves, and we have a few demonstrations to illustrate the properties we talked about here in the screencast.